Northridge, California, January 1994. For anyone that remembers that day, the images of devastation are frozen in memory. The earthquake destroys or damages infrastructure and buildings, but less than 100 people perish. Once again, modern seismic engineering has done well to protect lives. Yet this earthquake is the costliest in U.S. history. Even though they save lives, buildings are left uninhabitable and must be demolished. Can seismic engineering do better to protect that infrastructure and preserve communities in the aftermath of an earthquake? That is what a consortium of the National Science Foundation, the construction industry, engineers, and universities is asking with the Precast Seismic Structural Systems, or PRESS program.
The PRESS program is one phase of a cooperative US-Japan program on large-scale testing of structures for earthquake and wind resistance. This particular program, which involved cooperative research between Japan and the United States on different aspects of the seismic performance of precast concrete, initiated about 10 years ago when I developed a plan for the US program. The final phase is this large-scale test of a 5-story, what we call super assemblage rather than a building, to see how all the bits fit together and to make sure that when we test a real building that it does what we expect it to do.
The key to the success and effectiveness of the entire program has been the partnership of industry and academia.
Well, I think it's true to say that neither of the two sides in research or industry could manage without each other in this particular application.
Research universities provide, at least in my mind, or have provided a very valuable input into this process because they look beyond the box. Unfortunately, most professionals as well as industries tend to look within a prescribed box, and it's very difficult sometimes to really look at the trees without the forest, if you will. And that's what the research universities bring to bear.
The precast industry has been superb in its support of this program throughout. And in fact, that support has grown as the project has gone on. They've provided a tremendous amount of input into the conceptual ideas. They've provided a large amount, well more than 50% of the financial basis of it. And in the final phase, the construction of this building behind us, they have essentially carried more than 2/3 of the cost. They've been deeply involved in all aspects of it. And not just the PCI, but the local manufacturers have constructed the materials, done the precasting work, and bought it here in a timely fashion, even though they've been very busy with other work. Their support has just been extraordinarily good.
This project could never have been done without the research capabilities here at the University of California in San Diego. First of all, the people that they have here that are capable of organizing a program like this is absolutely essential to the success of the program. The credibility that the university has, and of course this magnificent testing facility, which I don't think is duplicated anywhere in the United States, all come together to interest a public body like the National Science Foundation in contributing large amounts of money to this kind of research. Without the setup here and the people involved here, I don't think we'd ever been able to have this kind of a research program for our industry.
The importance of industry in this whole project has just been enormous. They are essentially the client. They're the reason why we're doing things. They're the reason why we've tried to develop some of these new connections. And yet at the same time, they've also been a kind of sea anchor on us when we've gone too wild and said, hey, why don't we do it this way? They've been there to say, well, hang on, it's not economic, it won't make sense, you can't build it, it's just not practical. And that side of it, the kind of the balancing force side of it, has also been really valuable. And so often it's easy to invent some new connection or some new process for doing things. And if I don't see some of the major disadvantages in doing it industrially, they're very quick to remind us. But it's a very good process indeed, whereby it's almost like you look at a new idea with polarized light. You get one view from here, you get one view from there, and the more different views you have on it, then the more chance you have of finding out any flaws, so that when it comes to the end, you have a pretty bulletproof product.
The material which comprises this product is precast concrete, or precast, a hybrid system which combines the structural properties of concrete and steel to create a material with unique capabilities.
Precast pre-stressed concrete in a lot of ways is as different from concrete as wood is from steel. All concrete products have steel in them, regular what we call rebar, mild reinforced steel. Well, steel is best under tension. In other words, that you want some tension on that steel for it to be able to work as it was intended. Concrete is best in compression. So what we are doing with pre-stressed concrete, we use special strands of high tensile steel that is tensioned prior to pouring any concrete around it. We place concrete around that cable, and once the concrete has achieved sufficient strength, it actually bonds and holds on to that cable. So once it has that sufficient strength, we cut that cable. Well, at that point, that cable is trying to relax. It's trying to go back to its original configuration or shape, but it can't because it's got the concrete bonding to it. So the steel is in tension, and the concrete, because it's holding this steel, it's being forced into compression. So you have steel in its best application, tension, and concrete in its best application, compression, in pre-stressed concrete products.
Despite these inherent advantages, precast has not been traditionally used in seismic systems. PRESS will prove that with new designs, these advantages can be used to create better buildings.
Precast concrete is not used all that much in seismic design in the United States at the moment in seismic areas, and the reason for this has been poor performance of precast buildings with inappropriate connection details in earlier earthquakes. In particular, in the 1964 Anchorage earthquake, it got a bad reputation as a consequence of that. Subsequently, it has performed poorly in a number of other earthquakes. The Armenian earthquake of 1988 is another example, and even the Northridge earthquake here in the States of 1994, some precast structures again performed poorly, again because of inappropriate connection details. And obviously we're trying to change that picture.
The way we've done a lot of the design of this structure is to try to make the deformations, the places where the structure has to bend and yield, make those happen in the connections between the different pieces. Now, if you're building a cast-in-place concrete structure, then there are no kind of discrete connections between discrete pieces, and you don't really have that option. But with a precast structure, you can actually do that. And that's one of the kind of the lines that we've tried to take when designing this structure.
We are concentrating all of the inelastic action in the connections, which is quite different from the way in which precast concrete has been designed in the past, which has been emulating reinforced concrete, trying to make it exactly the same as reinforced concrete. We're not trying to do that. We're trying to make it quite different.
Standard construction for seismic systems requires that a building damage itself in order to save the lives of the occupants. Engineers do not try, in general, to keep a building intact after the earthquake. We allow structural damage. This is condoned by the code. This is what we're supposed to be doing in order to protect the lives of the occupants. The question is, how can you have a building that after an earthquake is still occupiable? That's not what people are getting now when they buy buildings that meet code, and any engineer will tell you that. These systems that we're testing here actually go a step further, and they're trying to minimize structural damage in the event of an earthquake.
To prove these new systems, the project's research tool will be the largest structure ever tested in U.S. history. It is known as the PRESS Phase 3 5-story test structure, and it will be put through the final trial in a unique facility at the University of California's Jacobs School of Engineering.
The Ttyl Structural Research Laboratories are a university research facility for the large and full-scale testing of structural systems and structural components. We have right now 4 large and full-scale testing laboratories which comprise the Ttyl Structural Research Laboratories, and with that it is the largest structural university laboratory anywhere in the world. This particular building is called our Structural Systems Research Laboratory, where we test actually full-scale structural systems, buildings up to 5 stories tall or bridges with over 100-foot length. We can test structures under simulated seismic loads here in our laboratories. For that, we really need very strong reaction floors and strong reaction walls, and this is really the key feature of that laboratory, that we have a 50-foot reaction wall against which we can load then up to 5-story full-scale buildings under simulated loads all the way to failure.
The test structure is intricately designed to represent and test a host of new and different methods to join precast components into a robust and resilient structure, a structure known as a seismic system.
In earthquake country, we need something called a seismic system. You need to resist the horizontal forces that the buildings get in the earthquake. And so you need a special system that holds the building up instead of letting it tip over like a house of cards. And what we're testing here are 5 different seismic systems. One of them is a wall system, and the other 4 are 4 different frame systems. By frame, I mean things consisting of columns and beams.
The point of this structure is to try to pull together a lot of the individual connections which have been developed over the past 5 or 6 years and tested as individual connections over the past 5 or 6 years. And the intention here is to try to pull those together in a structure and then load the structure as if it really were being hit with an earthquake, to observe the way that the connections really work when you have them in a real structure and they're all tied together and all the pieces have to work together.
All the systems being tested in the structure utilize an emerging new seismic design philosophy.
The design of the structure, or the prototype on which this test building is modeled, was using a new procedure called displacement-based design, which we've developed here at San Diego, essentially. And in this, we concentrate on trying to make the building respond to a particular level of displacement in an earthquake, rather than to have a particular strength. It's a bit like the concept of the reed in the oak tree. You know, the oak tree is very strong. If you make it stronger, it may still blow down in wind, but the reed will bend. But if the reed can't bend far enough, it'll snap. The strength's not so important. It's the ability to bend that far.
So this idea of kind of flexibility, if you like to put it that way, and avoiding some of the damage to the building is really a fairly new way of looking at seismic engineering, but I believe it's an important one for the future.
To test these new and important directions in design, the structure will actually undergo 2 batteries of tests. In the north-south direction, 4 different frame systems consisting of columns and beams will be tested. The east-west direction will test a shear wall system. This wall system is a key example of the use of post-tensioning for seismic resistance.
In the east-west direction, the earthquake forces are carried by walls. They're precast individual wall panels, so you can think of it just like a gigantic playing card made of concrete. And they're held down to the ground by what we call post-tensioning tendons. And these are essentially enormous rubber bands made of very high-strength steel. So they're not made of rubber, but they behave like a rubber band. And so you put the wall down and you have a tube down through the wall, or a duct, and you stress this steel through the duct, and essentially that kind of clamps the wall down on the ground. But if you push it hard enough, instead of something breaking, it'll simply lift off on one side a little bit, so the wall will kind of rock over like that, and then the big steel tendon down the middle will just pull it back up straight again when the earthquake loading disappears.
This post-tensioning is in a sleeve inside the wall, and it is not grouted, it's not bonded to the wall itself. And as the earthquake hits the building, the wall panel just rocks back and forth, and this post-tensioning pulls it back to its vertical position. The thing that's unique about the system that's tested in this building is actually this U-plate connection. The U-plate connection used here in the interface between the 2 wall panels actually rolls as the panels rock back and forth. The U-plate rolls and it dissipates energy as it yields right in this region of the U-plate.
The seismic frame systems will all be tested at the same time. The hybrid and pre-tensioned systems form the east side of the building, and the TCY and TCY gap connections form the west side of the structure. In the TCY gap system, There is a small gap between the end of the beam and the face of the column. The bottom portion of this gap is filled with grout to provide contact between the beam and the column. They are connected by two steel post-tensioning bars which run the entire length of the building, clamping the frame together. At the top of the beam, regular rebar extending the length of the beam and through the column is grouted in, except for a short length at the gap between the beam and column. When the beam moves laterally in an earthquake, the gaps at either ends of the beam open and close an equal amount, maintaining the dimensions of the frame system. Above the TCY gap connections on this side of the building, the TCY connections model a system that is similar to what is used in conventional cast-in-place construction. The TCY connection only uses rebar which is grouted in except for a short length at the beam-to-column interface. This connection is included since it emulates current use of precast beam connections. On the other side of the building, an innovative concept called Unbonded Prestressing is used.
In terms of the use of unbonded prestressing in precast structures, we might have a beam and another column on either side of it, and then another beam, which you can imagine each of these have been precast separately. And then we have a series of ducts or holes right through them that we stretch some high-strength steel. We pass the high-strength steel, we grab it at both ends and anchor it to the ends of the system. And that puts compression across all of the construction joints, all of the joints between the beams and the columns. Now, in previous pre-stressing of structures, normally the duct where the wire is passed through would then be grouted solid so that at all points along the length the tendon, that's the steel inside, is bonded to the structure, that's to the concrete. What tends to happen then is if you have a joint between, here's a beam on this side and a column here, as that joint opens up, it causes the pre-stressing tendon to gain a lot of strength and then go into the inelastic range. As it closes again, we lose some of the pre-stress. If the tendon is unbonded, we don't get that same increase in strength, but we don't get any non-linear behavior. We don't lose any of the pre-stress strength in the earthquake. And we've done a number of experiments which have proved this to be true on assemblages of beams and columns together, but this is the first time it's been put together in a total structural system.
Both the hybrid connection and the pre-tensioned beam, which form the east side of the building, use variants of Nigel Priestley's basic concept. The hybrid connections on the bottom 3 floors consist of beams which utilize unbonded post-tensioning strands that run the entire length of the building through a duct in the beams and columns. These strands are tensioned to clamp the frame together. Regular rebar at the top and bottom of the beam runs through the column and is grouted except for a short length at the end of the beam. When the beam moves laterally in an earthquake, the rebar yields dissipating energy, and the high-strength strands remain elastic, moving the frame back to center after the quake. Above the hybrid connections is the pre-tensioned beam system. It consists of long beams with pre-tensioning strands inside the beams, which are only bonded to the concrete at the ends. These beams are then set on one-story columns with reinforcing steel extending through the beams. As this frame displaces laterally, the unbonded strands remain elastic and recenter the structure after a seismic event. All these various systems have been carefully integrated into a structure that is designed at 2/3 scale so that it can fit in the huge Powell Testing Laboratory. Even though it is the largest lab of its kind in America, one of the challenges of the entire project is erecting the largest test structure ever built within the walls of this cavernous building. It was the charge of this man, Randy Clark, who directed a team of only 6 workers to erect the entire structure in merely 9 days.
The biggest challenge in erecting this building is the confinement that we're in within this lab, and the building fills it up quite a bit side to side. The structure consists of 8 columns, approximately 12 double T's, 20 floor slabs, hollow core and actuator panels, 4 wall panels, and the rest consist of several different types of beams. The heaviest piece was about 19,000 pounds, the pre-tension beams right up above us over here. We began the erection with the columns, And then we began to stabilize the structure by setting the beams along each floor at each elevation. And then we began setting the floor slabs. The complexity is definitely due to the reason it's a test structure. They have 5 different building type systems and different types of connections that they're testing all at once in this building. And the crew's done very well so far as to get every piece in with all the necessary parts.
The final steps in constructing the test structure are critical. Most important is the post-tensioning process, which will give the structure its innovative performance characteristics. But prior to the tensioning process, the joints and internal connections in the frame systems are grouted, establishing the tight tolerances between the frame elements and establishing the carefully calculated bonds between the concrete components and the internal steel, which will dissipate and control the seismic energy applied to the building. With the grouting complete, the tensioning process commences. The nearly 50-foot rods in the shear walls are tensioned, the rods which will flex and then restore the shear walls to their upright position. In the frames, both the rods and strands are drawn tight, putting the steel into the optimum state to control seismic loads. The feat of installing the largest test structure is not all that must be done. A tower to support the actuators for the wall testing is constructed. The tower must resist lateral force like the immense strong wall. To accomplish this in the confines of the lab, the narrow tower is stressed to the lab's floor with high-strength steel tensioning rods running the entire 50-foot height of the tower and deep into the floor of the lab. The rods are tightened to apply 4 million pounds of force on the tower, thus increasing its rigidity and resistance to lateral force. With the tower and structure complete, it is time for the researchers to instrument the structure for testing. The building components already contain a multitude of strain gauges which were embedded during manufacture. Countless connections are made to the sensors. Gauges are placed to monitor every movement and displacement and to provide the critical feedback which will allow precise control of the test's immense forces. And finally, a device for instant reference is installed on the structure. The core objective of the testing is to study the structure's response to earthquakes. But how are the effects of a seismic event created inside a lab? Here at UCSD, the cadre of seismic design and testing experts has the ability to employ a technique called pseudo-dynamic testing to faithfully recreate the effects of an earthquake.
The principle of pseudodynamic testing are that we combine computer simulation and physical testing in one experiment. So we have a full-scale model of our building essentially on the test floor. That's the physical component. And then we have a second model of our building in the computer. And in the computer model, we introduce then the actual ground motion. So we expose the building in the computer to a ground motion time history, which is pre-recorded from some other earthquake. And then we calculate in our computer model at a certain time step, let's say 1/100th of a second into the earthquake time history, we calculate the displacements at each of the 5 floor levels in our building. And then we send these displacement signals to our servo-controlled hydraulic actuators, which are arranged between the building and the reaction wall. And we move these actuators to these displacement levels. So we put the building in the calculated displaced shape.
The reason that we can slow the earthquake down in this form of testing and still have valid results is because we ensure that the sequence of displacements that we put on to the building is the same as would happen to the structure if it was tested at a faster speed, in other words, at the correct loading rate for the earthquake. And damage is related to displacements rather than forces or anything else. So if we take it to the same displacements that would happen in the real earthquake and in the same sequence, then we get the correct levels of damage. In fact, we get slightly more because it's more severe on a building to hold it at the large displacements for a period of time than it is just to achieve it for a fraction of a second and take it off. So it's slightly conservative, but it is realistic.
The simulated seismic events for the pseudodynamic process are derived from a select variety of actual earthquake records, among them the 1940 El Centro earthquake record. These records are then modified to ensure that the structure is thoroughly subjected to the required levels of seismic intensity and beyond. The mechanical means which will bring the earthquake record back to life are the actuators.
Well, these actuators are kind of like the rams you see on bulldozers moving the blades or on any kind of earth-moving equipment, except that these have electronic controls. For this particular test, we have 10 different actuators. We have 2 at each floor level. They come in different varieties with strokes from plus or minus 6 inches for the first floor, all the way up to plus or minus 24 inches for the top floor. The actuators on the first floor have a 165,000 pound load capacity. Those at the top floor have a 220,000 pound load capacity. This actuator here, for example, can push with a load of 165,000 pounds. That's something around the weight of like a 727 or a 737 jet aircraft. The actuators are kind of unusual in that we have this combination of really large forces, but yet we're able to control them down to very, very small displacements on the order of 1,000th of an inch. In the control room during the test, there'll be 5 of us. There'll be me. I'll be controlling the actuators and monitoring the health of the actuators and the data acquisition systems. There'll be Sri. He's monitoring what's actually going on during the test and conferring with Dr. Priestley to make decisions about what we're going to be doing next, whether the structure is behaving as we want it. There will also be 2 graduate students, Jim Conley and Stefano, and they will be doing close to real-time analysis of what's going on in the structure. The test actually takes place in several intermediate tests, and between those tests, these 2 graduate students spend a lot of time helping us make decisions about what we want to do on the structure next.
The structure is ready for testing. 12 years and countless hours of design and preparation have gone before. The testing begins. Time-lapse footage compresses the process. The team watches closely, monitoring the activity of the actuators as well as the response of the structure. A graphic display shows the amount of force the actuators are exerting to produce the target displacements. As it is subjected to the first loads, the structure makes evident its response to being displaced.
I think it's probably the pins, I guess, is it?
Something slipping in the pins, I think. Yeah. Okay, just hold it there for a minute.
The structure shows other evidence of its response to the seismic loading. Throughout the entire testing process, the team will inspect the structure for any cracking. The cracking doesn't affect the integrity of the structure, but the evolution and character of the cracks will help the team understand where and how forces were distributed in the structural elements, and how the structure is responding to seismic displacement. They carefully mark the occurrence of the cracks, eventually leaving the structure graffitied with a glyphic record of its performance. The structure successfully withstands the design-level earthquake requirements.
We are right on.
Now it is crunch time. It will be taken to the extreme. The displacement will be equivalent to an earthquake which might occur once a millennia. The top floor of the building will move over 11 inches from center, or over 22 inches back and forth, much greater than the movement which occurred in only a few seconds in El Centro in 1940. A few seconds which had devastating consequences. Here, the duration is a matter of hours. Yet the structure is actually subjected to more stress than in that real seismic event. As the test progresses, displacement becomes clearly evident. The flex plates in the walls bend as designed. The top floor moves further and further from center. The columns clearly leaning. At the height of maximum displacement, the researchers clamber over the structure. Floor by floor, they inspect and record evidence of the displacement's effect, so they can later correlate it with the data gathered by the instruments.
Yeah, we got the torsional crack in the floor.
You got a torsional crack now?
In the floor, yeah.
0.1 millimeter. Not going to get too excited about that.
Think bugger?
Time-lapse footage reveals how the pseudodynamic testing process eerily recreates the earthquake. The building experiences the first seismic wave, and then suffers a remarkable displacement, and continues to sway with subsequent seismic waves. But the walls, frames, and floors stand, and by all accounts, don't even approach a loss of integrity.
The lack of damage has surprised even me. It's been less than I expected, so it's just been great. It's a superb test.
It's amazing to me how little damage, how little distortion, things are able to move the way they're supposed to without anything bad happening. And if you had this kind of an earthquake and of course you're going to run out into the street probably when it's over, you're going to come back in and see architectural and interiors type damage, but the building structure is going to be fine and you'll be able to go right back to work. And I think that's amazing for an earthquake this size on a building.
If this building had been in Turkey, at Izmit, pretty much at the epicenter, I believe that this is about the kind of level of deformation it would have seen there, and at the moment it looks like it's coming through with barely a crack in it, which is, I think, what a lot of people out there would have liked to have been in a building like that.
There's no doubt that the level of shaking represented by what we've put onto this building is well above the design levels for buildings in California.
But it seems that the performance we're seeing at this displacement is actually much better than I'd even dreamed. Some of the very critical connections seem to be performing absolutely perfectly, and places where I expected to see some cracking in the concrete, not dangerous, but at least cracking, we don't seem to be seeing it. So the building is doing just astoundingly well, as far as I can see. And I'd be very happy to live in a building like this in a big earthquake. What else can I say?
Next in line for the battery of tests are the 4 frame systems joining beams and columns that make up the east and west sides of the structure.
In the frame direction, we've got 4 different structural systems connected by 2 different floor systems.
Each of those has anywhere from 6 to 9 different connections involved to provide that seismic resistance.
There's just more bits and pieces and more connections in the frame direction, so there's more potential for things to go wrong. We certainly hope that they won't, and we don't expect them to.
To accomplish the next series of tests, the entire complement of actuators must be moved from the reaction tower and attached to the huge strong wall so the building can be pushed in the frame direction. After shakedown and calibration, the researchers are ready to get underway. The first tests take the structure up to a level 2 earthquake record, equal to events which might occur once every 50 years. The various framing systems are performing well. This time-lapse footage clearly shows not only how flexible concrete can be, but it once again illustrates how effectively the pseudo-dynamic process recreates the dynamics of the earthquake record. The researchers then take the structure to the 500-year seismic event. The top floor is displaced about 10 inches from center, giving the structure a tilt, which is clearly evident, even to the casual observer. The structure easily survives the design level tests, but begins to reveal its secrets. Nigel Priestley comments on its performance and what is yet to come.
We've completed loading in the frame direction at the design level earthquake, which is equivalent to the maximum intensity design event for California. And the structure has performed well. The pre-stressed frame looks extremely good at this stage. There's very little spalling, the cracks are very fine. The other frame is not behaving quite as well. It's behaving fairly well, but we're having some problems with the beams slipping vertically at their ends where they butt onto the columns. We can see why that is. It's a small deficiency in the design approach. We need to be more conservative. The strength is still as high as predicted, but we're seeing some spalling of concrete, particularly in the frame on my right-hand side, which is not unexpected. We do expect the cover concrete to spall off, but the core, which is inside the reinforcing steel, to remain strong. It looks bad, but it's really not. The strength is still there. However, we want to go up to higher levels of loading, and there are some aspects which are causing us concern. Perhaps on the pre-stress frame, which is on my left side, what's happening there is that the floor system, which consists of double T beams, which is supported on the side of the main pre-stress beams, is causing them to twist a bit. So what we're going to do, and what we're seeing up there, is some welders providing some weld metal, and that will stop any further twist. It's something very important that we've learnt, and it's part of the reason for testing big structures like this, is that you always find out something unexpected which may change design practice in the future and improve safety. The next step in our testing, which we'll start next Tuesday, is to take the structure to levels of seismic displacements which are significantly bigger than expected in the design earthquake. The structure is designed for a maximum drift of 2%. What we want to do now is to take it to 3% drift, so a margin of safety of something like 50% above the design displacement, and see how it performs at that level. Assuming that it performs well there, we'll then take it up to 4% drift, or twice the design level. If it's still standing and intact at that stage, we'll call it a day, because we won't be able to apply displacements any bigger than that. We've run out of capacity in our actuators.
At that 3% drift, or 50% above the design displacements, the top floors are pushed close to 12 inches from center. At this level of displacement, well beyond what the framing systems were designed for, the various systems start to show their superior performance characteristics. The pre-tensioned beams and hybrid systems perform extremely well, without an increase in significant damage.
So it's close to 7/16 inch crack, and I think, as I said earlier, it's all concentrated here, and you don't get any crack on the beam at all. So it's performing as it was expected.
As in all good research, the team wants to probe the limits. They follow their plan to take the structure to 100% greater displacement than the design level. The top floor will be displaced 18 inches from center, the kind of displacement which might occur once every 2,500 years. The test gets underway. The researchers watch closely, monitoring the actuator systems and state of the structure. At the extremes of displacement, the team inspects the structure.
There's quite a lot of relative movement there.
Diagonal shear crack on the joint, the exterior joint.
These welds all look okay.
HE3S, one of the bottom rebar fractured.
Outside of it.
So outside one.
The test continues. As the strains increase, the structure responds with eerie creaks, cracks, and booms. To accomplish the extraordinary displacements, the team must pause the test and adjust the huge actuators.
The actuators at the third floor level don't have sufficient stroke when we're moving the top floor 18 inches. So what we have to do to accommodate that is, when we're at zero load, we push the actuator out a certain amount and put the pin into another location, which gives us 3 inches extra travel. So it extends the travel in each direction from 9 inches to 12 inches. We only need about 10 inches, but the 9 inches isn't enough. This is the maximum that we want to go to. In the first push to 18 inches, we got 4.5% drift, and the design drift is 2%. So we're pretty happy with that.
With the actuators reset, they are again set to task. The structure is reaching phenomenal displacement. The joints, where by design the stresses and damage are concentrated, start to show some effects. Concrete spalls, crushed at the joints between columns and beams. Rebar under tension snaps like immense rubber bands. Then, on the second full cycle of drift, something happens. Judiciously, the test is halted. The structure is allowed to settle.
Yeah,
I could fire those guys up and let them come to zero load.
Let's do that.
All right.
As far as, the test's completed now.
The team has taken the test far beyond the limits of expectations, into a realm which few structures have entered, and remained standing.
There was an earthquake in Turkey about 3 weeks ago which caused a huge amount of loss of life, and it was considered a great earthquake. Well, it had a magnitude of something like 7.4. What we're looking at is something significantly bigger with a significantly higher ground acceleration. The Turkey one had a maximum ground acceleration that I saw of about 0.3 G, which really isn't all that big. And what you're talking about here at this 4% drift is probably something with a ground acceleration on the order of about 0.6 or 0.8 G, possibly even a little higher. So you're talking about something with ground accelerations which are 2 to 3 times the one which just occurred in Turkey.
We've actually taken it to more than 100% past the design level displacements, and normally we would say that that is equivalent to probably a 2,500 year return period event.
If we think about what should we expect the building to look like at the end of this, well, I would expect it to look like a real mess. And in fact, quite a lot of it doesn't look like a real mess. Quite a lot of it still looks in remarkably good condition.
The wall direction has been a real winner, much better than we expected it to be. So that's the first thing that really comes out of it. The frame direction was a very much more complex area. We had 4 different structural systems involved in this. 3 systems essentially worked very well. They're the 2 systems on the pre-stressed side, and the tension compression yielding, which is at the top of the TCY system. The one that didn't perform quite as well was the TCY gap system. And that's been interesting. We've learned a lot from that. We know how to improve the performance there, and we believe that even though the performance has not been as good as we might have liked, it hung on there. And the point is that it was taken up to drift levels more than twice the design level.
I'm really, really happy with the results. We had incredible results with the wall direction. We all left here, at least I left here, feeling ecstatic about the wall direction testing. We came back, we tested the frame direction, which was much more difficult from both a complexity and a prediction perspective, and also from the actual results we got. Things weren't quite as perfect as they were in the wall direction, but still we got excellent results and have a lot of really good data to analyze.
It's going to take a long time before we really know everything that happened in this building.
After the structure is cleared of apparatus and instrumentation, project scientist Sri Sritharan takes the first step to understand what really went on in the test structure, revealing the effects of the seismic stresses as well as the performance and resilience of the designs.
The only damage that occurred to the wall system during the wall direction testing was just spooling of cow concrete in the corners here. You could just patch it up if you wanted to, and you're ready for the next earthquake. There were some minor cracks that we marked here that opened up and they closed when we removed the load. On this side we marked all the cracks, and we'll take a look at it on the other side. You will see there is no damage that you could visibly see. Right now we are looking at a hybrid joint system where the column to beam connection is established with unbonded post-tensioning, similar to what we have seen in the wall system. You could see there's no damage to the joint region where the maximum forces are transferred through. The damage what we see here at the top and bottom, in a design level earthquake, we will not see any damage like that. Part of the reason why we see this damage was that we took the structure to much larger displacements. At one point we moved the top of the column by 18 inches, and that's the reason we see some damage. And again, this is not structural, so we could easily patch up this damage as well. So we're on the first floor of the building now, looking at the second floor TCY gap interior joint system here. The TCY gap system performed as they're supposed to perform during seismic loading. However, we learned that the amount of compression that we provided here by the tension rod that passes through here at the bottom of the beam did not have adequate tension, and as a result we started to cause some damage to the bottom of the beam. And since we continued the test all the way to 18-inch displacement, you could see that we spooled off more concrete here than what should have been if we had had slightly more post-tension here. We are now looking at a pre-tension frame connection. Unlike the other precast system that we have looked at, here the beam is continuous, which contains the joint as well. So it runs from one end of the frame to the other end. In this system, the crack was supposed to develop between the joint and beam, even though the whole piece was constructed as one segment. And that's exactly what happened during the test. And you can see the crack develop right at the interface, and the crack opened up all the way to 3/8 of an inch for the maximum earthquake load being imposed onto the building, and now it's almost completely closed. The pre-tension system performed exceptionally well, as we expected from the design.
The success of the PRESS program has been a defining event, which promises to propel seismic engineering, design, and science forward. What lies over the horizon?
It's always tempting to believe that we've just about finished all we need to do in earthquake engineering, but I suspect that people thought that in the 60s. The prediction was then there would be no more need for doing any testing in 10 years' time. Everything could be done by computers. 20 years after that, we started to build these large-scale testing facilities because we realized that, in fact, we weren't getting the answers from the analytical models that were adequate. So I would hesitate to say that we're getting close to really understanding the way that structures behave in earthquakes. I think we're very much further on than we were 20, 30 years ago, but I think there's still plenty of opportunity for the young research students and young faculty members to cut their teeth on earthquake engineering problems.